Okay, sequences are sometimes used to solve some major problems. For example, big problem. Given a function, find x such that f of x equals 0. Okay, so this is one of the major problems you encounter when you are doing calculations. Okay, so one method is called the Picard method. Okay, so for example, if you use your scientific calculator, choose a function, choose an arbitrary number, and start pressing the same button over and over again, eventually the number on the screen stabilizes. Okay, so this is, you must have observed this for many times. There's a theory behind this. That's not a coincidence. That's explained by Picard's method. Okay, so here define g of x as f of x plus x. So add y equals x to the function and find x such that g of x is equal to x. Okay, so then, of course, if this is equal to x, then f of x will be equal to 0. So you will find this. So in order to do this, the method is the following. Let me draw the picture first, then it will be easy. So you see, this is the y equals x line. So this is what I add. This is x-axis, this is y-axis. Okay, I'll draw this like this. Well, it has to be just under this one. Okay. So it's the same. So this is y equals f of x. Of course, they are parallel to each other. This is the same thing, just shifted apart. Now this is y equals g of x. Okay. So let x sub 0 be any number close to the fixed point. So this is called fixed point of g, Okay, so g fixes it. So generally, when you are trying to find the root of something, you don't blindly attack the problem. You play with the function a little bit. You sketch its graph, etc. So you suspect around which point you will have this one. Okay, so this is the point you are trying to find. So you start with an arbitrary x sub 0, any number close to the fixed point. Okay, then x1 is equal to g x sub 0, x2 is equal to g x1. Okay, so xn is equal to g xn minus 1. So you continue this way. Okay, so if this sequence converges, it converges to this function. Let's see why. Okay, so this corresponds to pressing the same button over and over again. Okay, so you calculate this point. What is this point? X sub 0, g of x sub 0. Okay, so you go over here. The y coordinate is g x sub 0 here. Okay, g of x sub 0 is the y coordinate, but this is y equals x. So this is again g of x sub 0, the x coordinate. Okay, so this is your x1. You take this as your x1. Now you calculate this point. Okay, now this point again, you go here and you calculate this. Okay, so you see it eventually converges there. Okay, here of course I'm doing a little bit trick. The slope of this function around the root is less than 1. Okay, so that it is going like this. If it is larger than 1, you have to try something else. Okay, so for most functions this will work. For example, when you do it with cosine or sine, its derivative is again cosine or sine, so it's absolute. The slope of the derivative, the slope of the tangent line is in absolute value less than 1, so this will work. We also have Newton's method. In these methods, of course, the first thing is to find the root, and the second thing is once you start finding the roots, what is the fastest method to find the root? Generally, Newton's method is faster than most techniques. So let me go over Newton's technique. Again, somebody remind me 15 minutes before the end of the class, as always. Okay, so we'll have our usual quiz. Okay, so the second thing is Newton's method. With these methods, of course, if you desperately need to use them, there are studies on these things, under which conditions it will converge, under which conditions you have to try something else. But I'm giving this as an example of a sequence, okay, a useful sequence. So Newton's method is best described like this. So suppose you have a function like this, x, y equals f of x. This is y. Again, start with x sub 0 with any x sub 0 close to the root. Now, what you do in this case is you go up here. So this is x sub 0, f of x sub 0. You draw the tangent line. Okay, so tangent line. And you find this point. This point is x1. Okay, the point where the tangent line intersects the x-axis. Then you repeat this. Okay, then you go up. You draw the tangent line. This is now x2. Okay, so you see in this figure that it typically is very fast. It converges to the root very fast. So what we need is we have to write the equation of the tangent line. So equation is something like this. Y is equal to derivative at that point times x minus x sub 0 plus f of x sub 0. Okay, so this is the equation of the tangent line. So x1 is equal to x sub 0 minus f of x sub 0 over f prime x sub 0. Okay, so you see that f prime should not be 0 in this case. Okay, so you continue this way. Okay, so this is a sequence where it converges to the root of the function very, very fast. Again, this converges under certain conditions. In this picture, it is obvious. So again, you don't apply these things blindly. You draw, you sketch a graph, and you understand the behavior of the function. You understand how close you should choose it here. So for example, in this thing, if you choose it somewhere here, apparently this is something like this. If you choose this x sub 0 here, your sequence will converge to this root. Okay, so the general theory in this thing is you apply Newton's method. Sometimes it diverges. It oscillates back and forth, doesn't converge anywhere. And if it converges, it definitely converges to a root, but not necessarily to the root you are looking for. You can draw funny pictures where you start with a point very close to this root, but the slopes are such that it suddenly throws you on this side, and it converges to a root on this part. Okay, so this is a tool. It's just like a knife. You can do anything with a knife. Okay, but what do you do depends on you. The knife is not responsible with what you cut. Okay, so this is Newton's method. So let's use Newton's method to solve a particular problem. So I'll mimic this thing. So I'll try to find square root of 3. And this is going to be a demonstration of how induction is used. Okay, so using Newton's method. Okay, so f of x is equal to x squared minus 3. Solve f of x equals 0. Okay, so here you see f prime x is equal to 2x. You suddenly lost 3 there. And xn plus 1 is equal to xn minus xn squared minus 3 over 2xn. Okay, so you simplify this and you'll obtain something like this. xn over 2 plus 3 over 2xn. Okay. So you start with something here, x sub 0. Now, when we draw the shape of this, we know that the shape is like this. So no matter where I start from here, the tangent line will get me closer to here. So I don't try to be precise. I start with 5. My first approximation to square root 3 is 5. Okay? Let x sub 0 be 5. Okay? Now we want to show that. Okay, so we want to show that this sequence converges to square root 3. Okay, so that's what we'll do. So we'll use induction. First, show that xn is larger than or equal to square root 3. For our purposes, this statement is not necessary. For our purposes, first show that xn is positive, because eventually I'm going to evoke the monotone bounded sequence theorem. If the sequence is bounded from below, and if it is decreasing, then it has a limit. You see, once I know it has a limit, here I can take the limit of both sides as n goes to infinity. I get an equation for L. L squared will be 3. Everything is positive, so the limit, if it exists, is square root 3. That's very easy. So in order to show that it is bounded from below, I have to choose an easy number here. But just for demonstration purposes of certain techniques, I'm using this number. Okay, so if you just say xn is positive, it is clear. Okay, so show that each term is larger than or equal to square root 3 for all n larger than or equal to 0. N equals 0 is 5. x0 equals 5, greater than or this. So this part is okay. Okay. Now, for the general case, we have we use the following thing. If you have two positive numbers, their arithmetic mean is always larger than their geometric mean. Okay, so we put this here. You see that I have two terms. This is my A, this is my B. So xn plus 1 is equal to xn over 2 plus 3 over 2 xn larger than or equal to 2 times xn over 2, 3 over 2 xn. Okay, so this thing you see is, this part is square root 3. So xn plus 1 is larger than square root 3. With this technique, I didn't need the induction part, you see, okay, because this works for any n. Okay, so the second part is going to be induction, I think. Okay, so show xn is decreasing. Okay, so here, in order to show that this is decreasing, I want to show that this is positive. Okay, so we will work with this one. So xn is xn, and xn plus 1, I use this formula. So this is minus xn over 2 minus 3 over 2 xn. Okay, so you simplify this. You have xn squared minus 3 over 2 xn. Okay, so at this stage, I need this precise statement. Okay, xn is always larger than 0. It is bounded from below. But when I come here, I want to show that this is positive. So here I need to know that xn squared is always larger than or equal to 3. So this is positive. So xn is decreasing. So here I'm using the word decreasing in a loose sense. Okay, sometimes equal, sometimes strict, because we will eventually impose the monotone decreasing sequence theorem. In that part, what's important is that the sequence goes down, but it doesn't go up. Okay, so we don't need strict inequality to impose that theorem. Okay, so show that the limit exists. Okay, so the sequence is bounded from below and decreasing. Okay, so by monotone bounded sequence theorem, it has a limit. Okay, so this is how you show that the sequence has a limit. Okay, now final step. We know the limit exists. Find the limit. Okay, here take the limit as n goes to infinity of both sides. Okay, so what is it? Xn plus 1 equals xn over 2 plus 3 over 2 xn. Okay, so here you will have L is equal to L over 2 plus 3, 2 over L. You solve these things. Okay, so you'll get something like this. You get L squared plus 3 over 2L. So this is equal to this. Okay, so you have 2L squared equals L squared plus 3. L squared is equal to 3. And L equals plus square root of 3 since each xn is strictly positive. So it can't be negative square root 3. Okay, so this is the usual thing. So again, once more, in order to use this, I don't need this precise limit here to say that each of them is positive, gives me bounded. But that rough limit does not tell me that the sequence is decreasing. In order to get that the sequence is decreasing, I need that precise limit for the lower bound. Okay, so I show that the function has a nice lower bound. Using that nice lower bound, I show that the function is decreasing. Okay, now a decreasing bounded sequence must have a limit, and then algebra tells me that the limit is plus or minus square root 3, and then I use a little bit human interruption there, and I say the limit cannot be negative in this case. So this is precisely the limit. Okay, so this is one way of... Okay, not all sequences are easy like this. So we have this sequence, defined a sequence as follows. Another thing. Let this time let me use an. Let a0 be any positive integer. Okay. Then an is defined as follows. This is a n minus 1 over 2 if a n minus 1 is even. 3an minus 1 plus 1 if an minus 1 is odd. Okay, so do you recognize this? Did you see this anywhere? You are losing all the fun in life. Huh? Colas problem, yes. There are so easy things in life. So the first question is, what is the limit of this? Okay, so what is limit an as n goes to infinity? So this is the first thing. So you see, since it doesn't have a nice formula and it's claiming that for any, you start with any integer, you do lots of trials and errors. After much experience, you see that you always at some point go to 1. Okay, so if an is 1, then an plus 1 is 4. Okay, then an plus 2 is 2, and then an plus 3 is 1. So this cycle repeats. If you ever reach to 1, then you start going around this. Okay, so the question is, when do I get this situation and when do I get some other situation. Okay, so the claim here, so there's no money on this thing, but this is known as Collat's problem. And sometimes it's a conjecture. For any a sub 0, which is a positive integer, there is an index n such that an is 1. Okay, so no matter where you start, you'll always hit 1. Okay, so that's there are, of course, computer trials on this. So don't try this on the computer. It has been tried up to 10 to the power 60 or something. Okay, so true for all a sub 0 less than or equal to 10 to the power 60, I think something like this. Okay, so the number of atoms in the world is in the universe is 10 to the 80. So this is almost there. And one associated problem is this: what is given a sub 0, what is the smallest index such that it hits here? And surprisingly, this doesn't get very large. Very quickly, you go to 1. Okay, so the I think between 1 and 1,000, the largest index you can have is 100 something. Okay, so this is to learn some modesty. Okay, so with sequences, we get the feeling that we know everything. Okay, so this is just one thing which is easily described, but we don't know anything. Well, we know that we know this, but that doesn't help us. And surprisingly, well, maybe not surprisingly, there are books on this. There are articles, research articles written on this, even today. Okay, so this is a very interesting big problem. Okay, so I have, let me see here. So I did this one. Okay, I'll do 2 more sequences and then we'll have a quiz. Okay, so another sequence. A1 is square root 2. A2 is square root 2 of square root 2. A3 is square root 2, square root 2, square root 2. Okay. So this goes on like this. Okay. So eventually, in the limit, we have this infinite nested sequence of square root 2. So what is the limit? So what is the limit if it exists? Okay, so here we try to write a general formula for this. So in order to write a general formula, you observe that this thing is this thing, and this thing here is this whole thing here. So an is equal to square root 2 an minus 1. So if the limit exists, we can immediately find out what the limit will be. Take the limit of both sides. So assume the limit exists. Then take the limit of both sides. You will have L equals square root 2L. Then square this. L squared is equal to 2L. So L equals 0 or L equals 2. Okay? So this will not be happen, okay? Because this is increasing. Okay, but we don't know. Okay, so the limit is either 0 or it is equal to 2. So we check that the sequence is increasing. If it is increasing, well, it looks like it is increasing, okay, because here I take square root of 2. Here I multiply 2 by something larger than 1, and they take its square root. So this one is larger than this. So I suspect that it is increasing. But first, in order to show this, I need the following thing. Okay, so let me erase this and let me do this in order. Okay. So for the limit, first check that an is always less than 2. It cannot be larger than 2. Okay. So a1 is less than 2. That's okay because I have a number here. I know that it is less than 2. Then I take this one. Okay. I have an equals square root 2an minus 1. So an squared is equal to 2an minus 1 squared. Assume by induction, assumption, an minus 1 is strictly less than 2. Okay, so this is less than 2 times 4. Okay, so this is 8. So what did I get here? So no, not square. Yeah, you're right. Okay, so this is birdenbire her şey patladı. Okay, so this is 4. An square is strictly less than 4. So an is strictly less than 2. Okay, so we proved this by induction. Next, show that an is increasing. Okay, so for this we'll look at, so normally depending on the way the equations are given, you either look at the difference or the ratio. Here I'll look at the ratio, an plus 1. Okay, if an is increasing, this thing must be less than, larger than 1. Okay. Okay, so an is, no, I'll do it this way. Okay, so an is square root 2an minus 1, and here I have an minus 1. So this is square root 2 over square root an minus 1. Okay. Square root of an minus 1 is strictly less than square root of 2. Therefore, this is strictly larger than square root of 2. Okay, so this one, which is 1. Okay, so this tells me that an is larger than an minus 1 always. Okay, so the sequence is increasing, bounded, so has a limit larger than 0. It has a limit, and since it is increasing, it starts from a positive number and it is increasing. The limit cannot be 0, so L is equal to 2. Okay, one last sequence, again, to show that you can spend the rest of your life playing with these things. Okay, here it's not easy to write down what the sequence is, but we consider this thing. 1 plus 2, square root 1 plus 3, square root 1 plus 4, square root 1 plus 5. Okay, so this goes on like this. So I have all this infinite square nested square roots. Okay, so what is this equal to? Okay. So you see, you can stop here, square root of 1, then you can square root of this, square root. You can define a sequence in any way you like, so that as the limit, as the index n becomes larger and larger, the thing looks like this one. Okay, so this is, did you see this sequence before? This is again another of those famous sequences. Where you are losing life, where are you wasting your life? Okay, this is a sequence that Ramanujan asked in 1911, maybe a few years later, okay? So in order to find out what the limit is, I think Ramanujan gave a solution, but there are easier solutions, so I'll give you an easier solution. All you need to know is the following. Remember that we have x plus 1 square is equal to x squared plus 2x plus 1. Okay, so I'll write it like this. 1 plus x plus 2. Okay, your x squared is here, your 2x here. So I have this. Okay, now put x equals, I think you start with 2. Okay, you have 2 here, you start with 2. So here you have 3 square is equal to 1 plus 2. And here you have 5. I'll 5 write in red. No, you have 4, right? You have 4 here. I'll write 4 in red here. Now you put x equals 3. Then here you have 4 square. That is equal to 1 plus 3. And here you have what? 5. I'll write now 5 in red. Okay. So 5 square. So in order to have this, you put x equals 4. You have 5, 1 plus, and here you have 4. And I'll write this in some other color. 6. And then you have 6 square equals. Okay, did you see the pattern here? Okay, so is there a color that I didn't use? Okay, let's use blue. Okay, so you take this 4 square, take its square root and put it here. You take this 5 square, you take its square root and put it here. Okay, you take this and you put it here. You keep doing this, then you get this expression. Okay, so that expression is without this square root equal to 3 square. Because here I am not taking any square root. All the square roots are coming after that. Because here instead, in order to write 4, I have to take the square root of this. You see that now this is 2 times square root of 1 plus 3 something. That something comes with another square. So without this square root, I obtain the whole sequence here, which is equal to 3 square. Okay, so then you take this 3 square here, and since everything is under square root, you get 3. Okay? So next time, instead of going to Facebook, go to such places and have fun. Tamam işte ben de tecrübeli hoca. I stop at perfectly right time.